Hello friends, in this video also we will discuss about first law of thermodynamics. First of all, in thermodynamic analysis there are two approaches. First approach is system approach and second approach is control volume approach. Actually there are two types of processes, non-flow process and flow process. In non-flow processes, system has confined mass. Mass transfer does not take place. Only heat transfer could take place. But in control volume approach, that is in flow processes, a particular amount of mass enters the control volume and the same mass will leave the control volume. So at any instant of time. So far we will confine our discussion to steady flow process. Steady flow means there is no accumulation of mass inside the control volume or no any emptying of control volume. The system is running full. So you can understand that system approach is applied for non-flow processes generally, and control volume approach is applied to flow process. So system approach, in last videos also we had taken that in the derivation of first law and various processes. So we took the system approach in which a confined mass m was taken, a system of that confined mass m having thermodynamic coordinates p, v, t and some processes was done, and final the coordinates was calculated. So final coordinates, the initial coordinates would be p1, v1, t1 and final coordinates would be p2, v2, t2, isn't it? So today we will discuss about flow process and control volume approach. In system approach, a confined mass m was taken and thermodynamic coordinates were p1, v1, t1, enthalpy h1 and final coordinates were p2, v2, t2, enthalpy h2, isn't it? So now control volume approach for flow processes. So a particular mass m enters the system. This is the control volume. Suppose control volume is a hypothetical volume in which we consider various processes. So this is control volume and mass m with state point 1. This is state point 1. Entry condition, coordinates are p1, v1, t1. Why I wrote capital T1? Because it is in Kelvin. enthalpy H1 and velocity V1 and datum Z1, and corresponding values at exit condition, that is state point 2 are P2, V2, T2, okay, capital T2, H2, capital V2 and Z2. This is same mass leaving the control volume. Our case is steady flow. Work could be done heat could be transferred. So we will develop an equation for control volume or for flow processes. So that equation will be steady flow energy equation. Steady flow energy equation. In short form, SFEE, steady flow energy equation. Okay, so we will start its analysis. Okay, here only I am writing state point 1, P1, V1, T1, enthalpy is H1, velocity V1, capital V1 and datum Z1. So mass M is entering and we will analyze per unit mass. So with enthalpy H1, point 1 has enthalpy H1. Now it has velocity also, so kinetic energy capital V1 is square by 2 because M is 1 plus GZ1 and plus this heat transfer. So suppose we are taking positive heat transfer, that is system received heat Q. So plus Q, this heat will be received and that will be equated to the condition at the enthalpies or energies at second point, because energy can't be created nor it could be destroyed, because there is law of conservation of energy. First law of thermodynamics is law of conservation of energy. So equal to, that much will be equal to a work could be done. So if positive work is there, means system does work, so this much W joule would be consumed, so minus W. So it is customary to write W at right side with positive sign, equal to H2 plus V2 square by 2 plus GZ2 plus W. Look, this V2 and V1 are velocities and this is small v1 or new one, so don't confuse. Specific volume it is, and this is velocity for kinetic energy. Okay, and this Q could have plus or minus sign if heat is rejected, so it will be minus, because that much should be minus and then equated. And if work is done on the system, so it is negative work, and that increases the uh, enthalpy of the systems. So here it should be plus W, so here minus W. Okay, then it could be balanced. So because that much work is done on the system, so actually we supplied that much joule, so that should be minus. So actually that we supplied, it was not having, so here it should be minus, because at empty condition it was not, after that it was supplied. So be very careful in science. Positive heat, that is heat supplied, would be with plus sign here, and positive work, that is system does work, so at right hand side it would be with positive sign plus W. So that you remember, and rest you could do. If negative heat supply, that is heat is rejected, so minus Q, and work is done on the system, so this would be minus W. So here only all mistakes occur, all answers get wrong. So be very careful regarding the signs of Q and W, and all parameters should have in same unit. Some are in meter, kilograms, etc. So others should also be not in centimeters or other units. So it should be in one unit. Okay. Now we could write this. This is steady flow energy equation. This is steady flow energy equation. Now we could write H in the form of U plus PV, and further U in the form of T, that is CVT. So okay, I am writing step by step. So H1 means U1 plus P1 V1. Now rest is same, plus V1 square by 2 plus GZ1 potential energy plus Q, and in most generally it should be plus minus, and here plus minus. Okay, and if W would be written here, so this plus minus, and here minus plus W, so that now you can understand. Plus Q equal to U2 plus P2 V2 small v2 plus capital V2 square by 2 plus GZ2 plus W. And suppose we write internal energy in the form of temperature, so it will be CVT1, T1 in Kelvin. Don't put in centigrade, it would be wrong, because those enthalpy change we calculated from 0 degree Kelvin, plus actually this is P1, V1 minus 0. System did work, it had volume V1, or in flow system also that much specific volume, with that much specific volume it is entering, so that much work it has with it against P1 it occupied volume, so P1 V1 minus 0 volume at 0 degree Kelvin. So that much energy also it is taking with it, that pressure work or expansion work or PD work. So plus V1 square by 2 plus GZ1 plus Q equal to U2 plus U2 is CVT2 plus P2V2 plus capital V2 square by 2 plus GZ2 plus W. Now we could give numerical values in many case studies and many problems we could make for different devices, just like turbine, pumps, heat exchangers, or nozzles, diffusers, etc. So that we will do in another video. So today's topic is over. That is, we discussed about two approaches and this steady flow energy equation. This is very important. Be very prompt in that. Very careful at this stage. There should not be any mistake regarding heat transfer and work done. The sign of that. Otherwise, all answers will be wrong. Okay, and who wants to look my this derivation? H equal to U plus PV. So in another video that is named as first law of thermodynamics, in that it is derived, and so many more things. Okay, thank you.